Good morning. In the last class, we talked about time complexity and last few classes, in fact, where we learned about the big omega, big O, and big theta representations, lower bound, upper bound, and these are this big theta strict, tight, or rather a tight lower bound and upper bound. Okay. So today what I'm going to talk about is something else, and this is about space complexity. Okay. We said there are two types of complexities. One is time complexity and the other is space complexity. So let us look at the components of space complexity and how do we measure it. There are three basic complexities involved, and you measure space, instruction space, and which essentially the space required to store the compiled program. Okay. And you have a data space. Space needed to store all the variables and constants used in the program. Let's take an example. Let's say I have a function int do something. Of int a comma b comma c, and suppose I write a simple function like this: return a plus b plus c divided by a plus b star 4. This is some arbitrary function. Okay. Here a comma b comma c are variables and 4 is a number or a constant. Or a constant. Okay. So this is for, so you need one space when you're talking about data space, space for variables and constants, and we also need space for needed by variables like arrays, structures, etc. Then there is a third space called the environmental space. And what is this environmental space? When a function is partially evaluated. Consider a partially evaluated function. Okay, let's say I have a function module like this, f module f1 of int x, and let's say I write something like this: if x percent 2 equals 0, then return f2 of x, else return f3 of x, and if end module. Let's say I have this function like this. Okay. Now, suppose this condition gets satisfied. Suppose this satisfied. Then, let's say I have a function f module f2 of int x, and let's say I write something like return x star x end module, and let's say I had another function, maybe I just remove this note. Have another module f module f3 of int x, and let's say this returns 2 star x minus 1, something like that. Some arbitrary function. Okay. Now, if this condition is satisfied, then the control is transferred to f2. Transferred to f2. Now, what happens? Once f2 is completed, here, completed, then it must come back to this point, so that can be returned to the calling program. Okay. So you need addresses or pointers to return where return in F1. Okay. And these addresses must be stored. Okay. So you need extra space for all of this. So this is something that we realize. So this environment space, for example, now just consider I have a recursive function, f module, f2, and something here. And let's say int x, and if x equals 1, then return 1, else return x minus 1, or something like that. Okay. Sorry, return f2 of x minus 1. Let's say I have a recursive module. Then what happens here? F2 is calling itself. So the first time it's called, there is one, it goes to this particular function. So these are called activation records, and it will keep the return address in the first call of F2. Okay, where to return in the first call of F2, and so on until the thing is terminated. And you push it on what is called a stack, which is an abstract data type, which we'll learn about a little later. And once it terminates, for example, this will go back to the previous program, and so on until it finally comes to the first call, comes out over here, and comes out over here, sorry, and it comes out over here because x equal to 1, it will be here, and it will terminate the program. Okay, so this is something that, notice that this is something about functions calling other functions. This space is something that dynamically grows and is called the environmental space. Okay. Now, so this is something that is going to dynamically grow, and it's interesting that you have these static variables that are stored at one end and the dynamic variables which grow from the other end. And if you have a program like an infinite recursive function, these are your static parts, these are your dynamic parts, and it's not like midway or whatever. The pointers grow, and when the two pointers meet, you will be told that there is no space available. Okay. Stack overruns heap, as it calls itself. So your program is stored in the heap, and stack stores all these function calls and the dynamically changing variable names. Now let's look at the instruction space, and it depends upon the compiler used. The compiler options, target computer, and so on. And this is obvious if you see the same program. Then simple data types even, space required is a function of the computer and the compiler. Okay. I just want to show you one example, and let me show you a C program. Okay, I have two versions of, let's say this is my, okay, let me stop the share and share screen. So this is the C program that I have. Okay, so this is a sum of the n natural numbers. I've written 3 different versions of recursion, and I want to see how many calls it's making. Okay, now what I'm going to do is I'm going to use GDB to show what's happening. Before that, okay, now let me here. Okay, so notice that there are 2 versions of recursive sum executables. One was executed with a compiler option. Let me say GCC -G recursive sum.c -O recursive sum 2. Okay. And another one was without the -G option. Okay. Let me call it sum1. Okay. Now let us look at recursive sum start. Look at the sizes, sum1 and sum2 are what I created just now. Notice that here recursive sum2 is much larger than recursive sum1. What is the -G option? It creates what's called a symbol table so that I can debug the program. I can use it in the GDB environment. Whereas recursive sum1 does not load a symbol table. Therefore, you cannot debug it. Let me show you the example. Let me say file recursive sum1. I'm loading this. I hope many of you have looked at the GDB tutorial. I use Emacs as an editor, as I said, because it's my favorite. And let's say I'm using recursive sum1. So it loads symbol table. I said, yeah. Now I say break main. So it will stop at the main program. And let's say I say run, start from the beginning. And oh, it's already executed. Let me say I give a value of R. Yes. And why is it executing so fast? Okay. And this gives you the results over here. Now, when I ask it to list, it cannot list. Okay. List means I wanted to show the program. Now let me do file recursive sum. Okay. And I again run this program. I say continue. So it's the, notice that because the symbol table is there, you can see this pointer over here. I hope you can see this here. Then I say continue, and then it's waiting for me to give an value. I give 3 and I get the same answer. But the important point is, let me show you another once more. So it's the beginning of the main. That's where I broke. And I said that I can do an N here. And the arrow, for example, moves. And it's at this point. Let me give a value, continue here. And give a value of 3. Then the program executes. So the important point is, because it loaded all the symbols, it shows you step by step how this program is executing. Let me show you one more point. Now I can list it. It will show me the program. Okay. So this is the difference between various compiler options. And I want to show you something else. So you saw the sizes there. And that was a Ubuntu machine. And here, let's say I compiled it on my Apple laptop, and then you can see that okay, now if I do the same thing, ls minus l recursive sum star, notice that the sizes are quite different. Okay, sum1 and sum2, that is 12,000 here, and somewhere around 8,000, but the tile sizes are different. So the compiler makes a difference, and the operating system or the machine on which you run also makes a difference to the sizes and the compiler options that you are using. Okay, so this is the important takeaway from size analysis of programs. Okay, so let's get back to what I was talking about. And So now what we'll do is let us look at, I want to show one example. Let's say, what's this function here? Okay, there's my yeah. Let me share. Okay. Now I want to get back to this. Then, so importantly, what we say is, so as I already mentioned, if you're using Ubuntu 18.04, then with the appropriate GCC/G++ compiler, then here integer is 32 bits, short is 16-bit, and float is, I think, 8 bytes. Not sure, but and so on. And double is 16 bytes perhaps. Question mark. Let's check this out. So this is something that you must be cognizant of. So if you know that your number is only between, it's going to be at most 16 bits, then don't use integer, use short. Okay. So as I already said, we have stack, which holds the return address. Oh yeah, there are other things that I forgot to mention. Return address, it must also store local variables, values of parameters to functions, and all constants, reference parameters, and so on. Okay. Program stores the fixed part and the static allocation, and the program and static allocation for program, fixed size variables, constants. Okay. Variable part, get, depends on the problem. Instance, and gets dynamically allocated. I think you did this in the lab class. Allocate, right? You use malloc or clr. So if you look at the space occupied by a program, there is a fixed part and there is a variable part. Fixed, variable. Okay. And let's say I have a function like this, linear search int a and int x comma int n. So I'm looking for this element x in the array, let's say. Let me maintain my convention. F module linear search. I have variable int I equals 0, while I less than n, and a of I not equal to x, do I plus plus. If I equals n, return -1, else return I. Okay, so you have a program like this. End module. Now, what is the space that's going to be occupied for this? Let's assume 2 byte for integer. Now, when I'm passing A, I'm only passing an address of A, okay? Like this. So this requires 2 bytes because I'm not I'm not copying the entire array. It's only the address of the array that's sent in C. And then there's an address for the variable X, 2 bytes. Then, oh, here I am, okay, let me get back to this. Then the value N, I'm sorry, I think I'm passing this as a value here, right? Yeah, since I'm passing it as a value, X, 2 bytes, and I, 2 bytes, and integer constants, 0, -1. So these are the two integer constants that we are 0 here and -1 here. Therefore, I have 4 bytes for them. The total space required for this function is 12 bytes. Now A must be large enough to hold n elements. Okay, but we are not worried about A in this function call because the space for A is allocated in the calling program or function. That is, I have somewhere, let's say in your C program, I have a main and I have int A of 10, it's allocated over here, and I do linear search of A comma X comma 10. Let me change this. Just want to find whether this value is present, A comma 5 comma 10. Then in the main function, A will be allocated. So the function space for this function is only this much. There are other things that you also do when you do space complexity. During my time, I must tell you that we thought we were doing machine learning at that time with 64K of RAM. And I had an 8-bit machine to work with. So what we would do is we would load one function in, and once the function is finished, we would load the other function. These are called overlays. Okay. So what we would do is then when you count space, let me give you an example. Let's say I have two functions, fun1 and fun2, that are overlaid. These are things you don't need to do nowadays because you have huge amount of RAM. Then whichever takes larger space, you would allocate that much as the cost of the space required for the function on your program. So this kind of completes the part on space complexity. And we will not be dealing with this anymore except to count it. But I must tell you, when I started as a programmer in 1978, I used to worry about where every byte of my program went, where every byte of my variable was stored, and save on every piece, because I was doing machine learning at that time, and you need large amount of data. So you're loading from disk, then pushing it back on disk, loading it back, and so on. Okay, so we'll stop the first part over here, and